Hi guys, welcome back. In this video, we are going to discuss first chapter of basic electrical and electronics engineering subject. First chapter consists of two parts. First part is DC circuits, and second part is AC circuits. Specifically, AC one phase circuits, I guess, single phase circuits. In our next few videos, we are going to discuss on a whole our discussion will be on these topics itself. As part of this DC circuits, our first topic is Kirchhoff law. We have two laws, two Kirchhoff laws, two Kirchhoff laws. One is for current law, one we known as current law, and another is known as voltage law. We will discuss about those laws now. First, Kirchhoff law, what it states. Kirchhoff laws are more comprehensive than Ohm's law and are used for solving electrical networks which are not be readily solved by later. Like if we have like only one resistor and one voltage source, then we can use this what we call Ohm's law for by using V is equal to IR, we can find whatever we want. If you know two variables, we can know another unknown thing. But for network of resistors and network of like potentials we have in a circuit, then to carry out calculations of voltage, current, and resistance, we need special laws. The special law is introduced by Kirchhoff. Kirchhoff's laws are more efficient than Ohm's law in solving the networks of in circuits. Not only circuits, it can be used for solving like uh, RLC circuit, LC circuit, every type of circuit. Kirchhoff's laws. Now we will go to the Kirchhoff's law. What is meaning? Kirchhoff's laws, 2 in number, are particularly useful in determining the equivalent resistance of a complicated network of condensers and for calculating the current flow in the various conductors. Like Kirchhoff's laws are mainly useful for finding R equivalent. By using this R equivalent, we will find by using Ohm's law, V is equal to IR, we will find current through the circuits. This is the basic motto of the Kirchhoff's law. We have two Kirchhoff's laws, right? First one is Kirchhoff's current law. What it states is in any electrical network, the algebraic sum of current meeting at a point is zero. It in the sense the total current entering into a junction is equal to the total current leaving the junction. That in the sense, just consider a junction. Just consider this as a junction. According to Kirchhoff's current law, whatever the current entering, like I1, I4, these are entering currents, right? I1 plus I4 equal to like sum of current leaving the junctions, right? I5, the things leaving. I5 is leaving, I2 is leaving, I3 is leaving. Just I5 plus I2 plus I3. That's what written over here, right? This is the basic law, basic Kirchhoff's law. This is how we use Kirchhoff's current law. In whatever circuit we might be solving, then if you're considering there are a lot of nodes leaving from the this node, this junction, then we will take the sum of currents entering into the node and sum of current leaving out from the junction are equal. This is simple Kirchhoff's law statement. That's it. We will came to know about it when we solve problems. We will solve problems on this topic also. Then we will get to know it. And another law is Kirchhoff's mesh law or voltage law. Kirchhoff's mesh law or voltage law. It's also known as KVL. In KVL, in any electrical network, the algebraic sum of product of currents and resistance in each of the conductor in any closed path in a network plus algebraic sum of EMFs in the path is zero. That is, if we have a closed circuit with potentials, with voltage differences and with some resistance current flowing through it and some other product of current, yeah, and some other voltages and some other resistance, some other resistance. According to KVL, the sum of potentials over all the elements in a closed circuit is equal to zero. That's what written over here. That is summation of IR plus summation of EMF equal to zero in a round mesh. That is KVL. That's the thing stated by KVL. It should be noted that algebraic sum is the sum which takes into account the polarities of voltage drop. We have this statement stated that we have to consider the polarities of voltages before summing it up. Like if we have voltage drop in voltage, then we have take minus EMF. Yeah, I will discuss this thing next slide. Just be with me. Yeah, just I have taken these points in this slide. Determination of voltage cell. In applying Kirchhoff's law to a specific problem, particular attention should be paid in algebraic sign of voltage drops. That's what I mentioned in the last slide. Voltage drops, algebraic signs of voltage drops should be taken care. Sign of battery EMF. We have, according to KVL, sum of IR plus summation of EMF. EMF in the sense electromotive force, right? Voltage will be measured in EMF units. Right? Summation of IR plus summation of EMF equals 0. Right? First, we have to consider the sign of this IR and we have to consider the sign of this EMF. First, we are dealing with sign of battery EMF. The rising potential should be taken a positive sign. Okay? If we have gain, voltage gain, then positive sign. Voltage drop, that implies negative sign. That is how we can know that we'll gain some voltage, how we know that we drop some voltage. Just follow the statement. That is, if we go from negative terminal of the battery to the positive terminal, in the sense, if you are going smaller sign to bigger sign, smaller sign to bigger sign, it is negative symbol, it's positive symbol. In batteries, we use these notations. That is, if you go from negative terminal of the battery to the positive terminal, then rising potentials. If you're going like this, it's rising potential. Then we will take plus. If you're coming in the opposite direction, if you're coming in opposite direction, we will take negative. Okay, right? That's what is written in this next statement. The sign of the battery EMF is independent of the direction. This point states that, like, whatever might be the direction you are going, the EMF of the battery will be positive itself. If you are going from positive to negative, that in a sense it's not a negative voltage source. It's a positive voltage source only. We are considering it in the negative direction. That's it. Now the sign of IR drop. Now in the previous slide I have explained about the sign of EMF of a battery. Now we will take the sign of the IR drop. Now take the case of a resistors. If you go through the resistor in the same direction of the current, then there is a fall in potential because current flow from higher to lower potential. In the voltage shall be taken negative. However, if you go direction opposite to the current, then there is a rise in voltage. Hence, the voltage rise should be given a positive sign. Just think of the scenario. It is a circuit, and if you are assuming that if our current is flowing in this direction, and if you are taking the KVL in the same direction of the current flow, if the current is flowing in this direction, and if you are considering our KVL to be in this direction, if you are taking the KVL law in this direction, in a sense we are going along with the current in the same direction of current. If you are going in the same direction of current, then we have to take minus IR. Whatever might be the current, whatever might be the resistance, we have to take minus IR. In some cases, we are going here, we are going like in the same direction. If you are considering our KVL to be in this direction, like I will change a color. If you are considering our KVL to be in this direction, then we will take plus IR because in our assumptions, the current is flowing in this direction. This is the direction of current flow, and we are going against the current flow. So we are going to take plus sign. That's the trick. And now I'm going to sum up all the potentials in the whole circuit. Just consider uh, I4 is leaving from here, and some I is coming here from node A, entering into node A. According to KCL, Kirchhoff's current law, at node A, I4 plus some IA, let it be IA, entering into node A, is equal to I1, right? Same thing, we are going to apply over here, KCL over here, and we are going to form some equations. And we are going to apply KVL in the whole loop. Then we will get one of the equation. Then we will solve all the equations. Like here we are going to get 1, 2, 3, 4, and 5. five equations. We are going to get five equations, and the current flow in the, like, it won't be same because everywhere the current is entering, right? And like I will be the current just traveling from this potential, just traveling out from this potential, and it's passing through R4, and some currents are getting introduced. Now it is one unknown. IA is, I mean, IA be the inlet from the node here, right? IA is another unknown. IB, IC, ID. We have total four unknowns, and we are going to get four equations. One KCL, two KCL, three KCL, four KCL, fifth KVL. Five equations, five unknowns. If we solve that equations, we will get this IA, IB, IC, ID. That's it. This is the typical problem of an Kirchhoff law, where we are going to use all both the laws of Kirchhoff. One is KCL and another is KVL. Uh, the next topic is like superposition theorem in circuit analysis. Superposition theorem in circuit analysis. First question, the next question we are going to discuss is superposition theorem in circuit analysis. Before going to discuss this topic, first question we have to ask is where we are going to use, where we are going to use this theorem and why. Let us ask ourselves where we are going to use this theorem and why we are using this theorem. For this question, and just consider where we have two voltage sources. Here we have in this circuit we have two voltage sources. Even if we are going to apply this last KCL or KVL, we will get the answer, but it's very lengthy process. Just considering two voltage sources and taking many equations, it's a lengthy process. Two, like, if you don't have this voltage over here, we are going to consider these two things are in parallel, just like that, right? We are going to draw like this. These two are in parallel, and these are equivalent, and this is in series. And we will add up. We will find. We are able to find this are equivalent, and we can easily apply KVL or KCL, something like that. We can find it out. But when these voltage is introduced, it is difficult for us. What we call to assume that these and these are in parallel or series. That's why we use this superposition theorem. In this superposition theorem, we have four steps. I will discuss one by one. First step is replace all the power sources except one. In the sense, first step is replace all the power sources except one. According to first step, in this problem, we have two power sources, right? We have to replace every power source with zero, and we have to consider only one power source. I'm going to replace this, and I'm considering the whole circuit with this potential only. Then I will find this R equivalent, and I will find flow to the flow of current through the circuit. And next step is calculate the voltage and current due to the each individual source. I have calculated that what we call first with first voltage potential. I have calculated all the currents and all the voltages across all the resistors. Now step three is repeat step one and two for each power supply. Like in first step, what we did, like we have neglected all the power sources except one power source. In step two, we have calculated all the voltages and currents across all the resistors due to that specific EMF, right? Like that, we are going to consider every single power supply, and we are going to neglect every other. Like in this step, we are going to neglect it. We'll change the color. We are going to neglect it, and we are going to consider this. And I will find all the currents, voltages across all the resistors, and like it's the third step. And the fourth step is superpose the individual voltages and currents. Like for every power supply, for first power supply, we got some I, comma V, comma R values, right? For second power supply, we got some I2, comma V2, comma R2, right? For n power supplies, we might have got IN, VN, comma RN values respectively. Now we are going to add up every single I values for whole current through the circuit. For I through circuit, we will add this I1 plus I2 plus I3 and so on up to IN. For R equivalent, we will add up all these R's, R1 plus, R2 plus, R3 plus, and so on up to Rn. That's it. This is a simple superposition theorem. Just don't get confused by looking at those heavy names called superposition theorem. What might be those terms? What might be the content behind it? Just try to approach it in a simple manner. We will get everything. That's it, guys. We have discussed the basics of DC circuits. I think this is up to. I think this is all for this video. Meet you in the next video, guys. Bye.